Assalamualaikum and good afternoon, everyone. Today we are going to present about the disaster management system, which focus on the smart monitoring system and the smart forest fire mitigation system. Next slide. So, introduced to our team, Ana Kamila, Chazriel Mukris, and myself, Ashakir. Next page. This is the table of content, which is the first one will be introduction, IoT architecture, design and component, network topology, security and reliability, and AI integration. For introduction, next. So the objective of our the objective of our report will be to design and justify a robust IoT network for integrated disaster management, which the application is for smart flood monitoring and smart forest fire mitigation. So the system capabilities will be real-time data acquisition, secure communication, and predictive analytics. So this report will provide a key features of multi-tier IoT architecture, optimized communication protocol, cloud-based data storage, and analytics. For the last key features will be optional AI for predictive modeling and anomaly detection. The next part will be the IoT architecture design and component. There's 4 layers, which is the sensing layer, gateway layer, network layer, and application layer. For the first layer will be the sensing layer, which has the purpose, uh, the real-time environmental and hazard monitoring. So the deployment is for flood-prone and pit forest area. So for the sensing layer and the flood monitoring sensor, we will use ultrasonic pressure transducer, which is the water level, rain gauge, soil moisture sensor. However, for pit fire mitigation sensor, we will using temperature and humidity sensor. And the next sensor will be the CO carbon dioxide and the CH4 gas sensor. For in the sensing layer, we will use low power microcontroller, which will power by solar or lithium battery powered lithium battery. For the next layer, it have the function of data aggregation and processing. We will using the short range, low range one, which have the capabilities of filtering and time stamping, anomaly detection, local caching for data reliability, and uplink sensor or satellite one. So the features will be it has weather resistance, backup power for resilience. For the next slide, it will be the cloud and application layer. So for the platform example, we use AWS IoT Core, Google Cloud IoT, Azure IoT Hub, because it have the core function of real-time dashboards and analytics, and historical threat analysis, and automatic alerts, which through SMS, email, or apps. For the last core function is the GIS integration for hazard mapping. So for this cloud application layer, in the data management, it can be scalable, secure cloud infrastructure. And this, for the last layer, is the actuation layer. The purpose is to automated disaster response. For fire mitigation, activate water pump or fire suppression system. For flood control, trigger drainage valve or barrier gates. So the integration is linked with cloud triggered alert and AI risk model. So for the next slide, I will discussing about the communication protocol overview. So from sensor to gateway, we will use low range 1, chosen for its long range up to 15 km and ultra low power consumption, which is essential for battery-operated sensor deployed in remote or rural floodplains and peat forests. Studies confirm that low-rate-based systems are effective for search and rescue and disaster response. For the gateway to network server to cloud, we will use the MQTT protocol because it has a lightweight header. It uses a 2-bit fixed header, which minimizes data overhead and is crucial for devices with limited bandwidth. It has small code footprint. This makes it ideal for gateway device with limited processing power and memory. Or the next point will be the efficient publish prescribed model. This model ensures minimal overhead and high scalability, allowing many devices to communicate efficiently without direct peer-to-peer connection. And the last function will be the reliable messaging. It's offered 3 quality of service level to ensure message delivery even over unreliable and intermittent connection. Or the last protocol is the cloud service, the HTTPS or REST, used for the web-based user dashboard and API interaction, leveraging established security and web standards for high-level data access and control. For the next part, will be explained by Aina.
Yep.
So I pass the...
Okay. Yeah, I'll be taking over the topology part. So before that, I want to get into our design considerations. For wireless connectivity, we choose LoRaWAN because it's suitable for our use case. It's ultra low power, and it can last up to 10 years on a single coin cell battery, which is important for us because since our deployment is outside, it's also long range. So LoRaWAN gateways can transmit and receive signals over a distance of over 10 km in rural areas and 3 km in dense urban areas. So for ease of management, firmware updates are sent over the air. So you don't actually have to go to the site. So it's to ease the management side. It also provides seamless roaming, seamless handovers from one network to another. So for scalability, it provides high capacity. So LoRaWAN network service can handle millions of messages from thousands of gateways. So as you can see, if we were to add more IoT devices, I'm going to go through the architecture later. But if you want to add more, it's technically no problem. So if there is a need for public and private deployment, it's easy to just use the same hardware and software. It uses a license-free spectrum, so there's no need to pay expensive frequency spectrum license. So you can just deploy it. And it's low cost. The infrastructure is quite minimal. It's even the end nodes, the sensors are low cost, and it's open source software. I'm going to go into the architecture because I feel like this is very new to most of us. So it consists of end devices, which are sensors and actuators. So they communicate with the gateway through using LoRa modulated wireless messages. They receive and send messages this way. So it uses RF frequency, radio frequency. And then the gateways, it receives messages from the sensors and actuators, the end devices, and forward them to the network server. The network server is actually on the internet. So it's a piece of software running on a server that manages the entire network, manages the gateway and devices, applications, and users, and the entire LoRaWAN architecture. So how does it work exactly? The end devices communicate with nearby gateways. Each gateway is connected to the network server. So it uses an Aloha-based protocol where devices don't need to connect to specific gateways. Messages from end devices are picked up by all gateways within range, and all received messages are forwarded to the network server. So if there's any duplicates, the network server performs message deduplication, so it only keeps one copy and discards the duplicates. The final part of the architecture to tie it all is the application server. So it operates, again, like the network server, it operates on a fully IP-based networking. So it processes and visualizes the data using protocols like MQTT and HTTP. So this is where we connect balik to Shakir punya point, because that's the subscriber recipient. That part is the one that's like alerting to the emergency response by gathering the information collected from the census. So that's how the whole picture is. Because our deployment is going to be outdoor, so LoRaWAN provides actually both indoor and outdoor, but for our case, it's going to be outdoor. So it uses outdoor macrocell gateways for wider coverage. So these gateways have higher receiver sensitivity, making it suitable for rural and even urban areas. Common mounting locations include somewhere higher up, like cell towers, tall building rooftops, and metal masts. And then outdoor gateways typically use external antenna, for example, fiberglass connected via a coaxial cable. So for one access, so you might be wondering why are we using separate things. It's because for the primary wireless communication is LoRaWAN, but then LoRaWAN architecture only knows like LoRaWAN things. So because the gateway still needs to bridge to the IP network, so it still needs one access to send data to the internet. So our primary one link for the gateways is using for DLTE because of its wide coverage, decent bandwidth, and quick setup. So for our backup, we're using satellite. So it's a automatic failover mechanism. So it's not like just calling back to what someone did. Their group did dual home. So we're not doing that. So if the LTE goes down, it automatically fail over and activates the satellite connection. So because it's suitable for remote sites, again, we're doing it outside. So this is the most applicable one. And it's not the primary link due to much higher latency. And as you can probably guess, because it's outside deployment, we're not going to use fiber, although it's really fast and all. It's really expensive and like, yeah, it's a long range deployment. So going into the network topology. So to summarize, the gateway connect to the default gateway. Default gateway as in LTE provided by ISP to reach the outside network. So again, like I said, since the end devices communicate via radio frequency directly to the gateway, they don't actually need IP addresses. So it's only until when they reach the gateway will it go outside. And then, yeah, it connects to the network server. An application server is reachable once the gateway has internet access. And then the gateway, the plan is, since it's long range, actually one gateway is actually enough to cover a wide area. So our consideration is maybe we find affected areas and geographically put gateways in different areas that's affected by the disaster. And then, but yeah, it's long range. So like, even though it's like, yeah, what 15 kilometer earlier, it can still accommodate a lot of sensors in a wide area with just one gateway. But yeah, as I said, it's quite easily scalable. Okay, Cedro.
So moving on to security and reliability, which is the cornerstone of any mission critical systems. For a disaster management system, these are not just features, they are absolute necessities. Our goal here is to ensure these systems are both robust and trustworthy. So why are security and reliability non-negotiable? Because these are mission critical systems where failure is not an option. The consequences of failure can be severe: loss of life, property damage, environmental catastrophe, and a fundamental loss of public trust. Therefore, our model is built on a multi-layered strategy where security protects our data and systems from malicious attack, and reliability ensures the system keeps running when it's needed the most. Next. Our first pillar is a multi-layer security framework designed to protect data and access at all times. This is built on the core principle of CIA triad, which is confidentiality, preventing unauthorized access to our data; Integrity, ensuring that data cannot be tampered with or modified unauthorized. And availability, making sure the system and its data are accessible precisely when needed during a disaster. Next. Let's see how we implement this from the sensor all the way to the cloud. For data integrity and confidentiality, we implement end-to-end encryption. From the sensor to the gateway, we use LoRaWAN with AES 128 encryption. From the gateway to the cloud, we secure the MQTT protocol with industry standard TLS SSL encryption. For device authentication, sensors use LoRaWAN's over-the-air activation or OTAA for secure network joining. Our gateways authenticate with the cloud using robust X.509 certificates. Finally, for user access control, we implement role-based access control or RBAC to limit system access based on user roles. Furthermore, we enforce mandatory multi-factor authentication or MFA for all users, adding a critical second layer of security. Our second pillar is system reliability and fault tolerance. We are designing for resilience in the harsh environment where these systems will be deployed. Our objective is simple. The system must operate and survive through redundancy and proactive monitoring. We focus on three key areas, which is connectivity, power, and network monitoring. A reliable system has no single point of failure. For connectivity, we use a robust, redundant approach. Our primary link is LoRaWAN combined with a cellular LTE backhaul. We have a backup one failover with multi-carrier SIMs. We also integrate satellite IoT connections as a final redundancy. For power, we ensure sustainable energy management. Both sensors and gateways are equipped with high-capacity batteries, and to keep them perpetually charged, we pair them with solar panels, making the system self-sufficient. Our approach to reliability is proactive, not reactive. For fault tolerance, we design our gateway coverage with about 20% overlap. This means if one gateway fails, a sensor can automatically reassociate with a neighboring one, ensuring data still gets through. For proactive system monitoring, we implement heartbeat monitoring. Our gateways periodically send "I'm alive" messages to the network server. If a gateway goes silent, our system triggers automated alerts, immediately notifying the operations team with the gateway's GPS coordinates for a rapid dispatch. The technologies we're selected are not just theoretical. They are proven in real-world scenarios. For wildfire detections, organizations like DHS Science and Technology Directorate are using similar AI-assisted sensors. Companies like Dryad Networks are already deploying commercial-scale LoRaWAN mesh networks in forests powered by solar energy. For flood monitoring, LoRaWAN-based flood monitoring and warning systems are already in use, providing real-time water level data and sending mobile app notifications from ultrasonic sensors. To bring it all together, we see security and reliability as two sides of the same coin. A safe system must be one that works. If a device is offline, its encryption is meaningless. Conversely, a reliable system must be secure. High uptime is worthless if the data being transmitted is compromised. Our design integrates both seamlessly, a defense in-depth security model layered atop a proactive, redundant architecture. This builds a robust system capable of withstanding the immense challenges of disaster management. Next. This brings us to the final transformative layer of our system, which is AI integration. Here we have from simply collecting data to generating predictive intelligence. This is about transforming monitoring into proactive management, significantly enhancing both our smart peat forest fire mitigation and smart flood monitoring systems. So here we talk about the journey, which is the IoT architecture provides the foundational nervous system, a vast network of sensors gathering immense amounts of real-time environmental data, whereas AI and machine learning acts as the advanced brain. It processes all this data to create predictive insights and can even automate responses. The main advantage here is a fundamental shift where the whole system evolves from reactive monitoring to proactive intelligence. Our first AI application is for smart peat forest mitigation. The challenge is to detect peat fires in the early smoldering phase, what we call as seeing the unseen. Our AI solution is a fire risk prediction model. Its objective is ambitious, which is to prognose the probability of a fire in ignition before it even happens. Here's how the fire prediction model operates. It analyzes multiple input data streams with real-time sensors data like soil moisture and gases, historical fire incident data, and geospatial and weather data from satellites and forecasts. This data is fed into the AI model, a powerful classifier like random forest or XGBoost, which is excellent at detecting the subtle nonlinear patterns that leads to fire. The output is a dynamic fire risk probability score categorized as low, moderate, high, or extreme for each forest zones. This then triggers automated action, such as instructing directed irrigation system to preemptively dampen high-risk areas or dispatching pre-alerts to ground patrols for surveillance. Our second AI application is for smart flood management. The challenge here is more complex than just predicting if a flood will happen. We need to predict when, where, and how severe it will be. Our AI solution is spatial temporal flood inundation model. The goal is to provide targeted, impactful based early warnings that empower communities and responders. This model runs on our digital service cloud platform. It ingests various input data, including hydrological data from our sensors, topographical information like digital elevation models, and historical flood maps. The AI model itself uses a combination of techniques, an LSTM or long short-term memory network, is perfect for long-range forecasting of water levels based on time series data. This is combined with hydraulic or other ML models to generate accurate inundation maps. The final output provides impact-based warnings such as the predicted arrival time of flood wave and dynamic maps showing flood depth and extent. This translates into actionable intelligence, helping authorities identify dangerous roads and infrastructure at risk, and optimize public safety updates in real time. So how do you make this happen technically? It all comes together in the cloud. A data pipeline using services like AWS IoT Core or Azure IoT Hub feeds data into a centralized data lake. Our AI engine built on managed ML services like Amazon's SageMaker or Azure ML. It handles the heavy lifting, which is training, versioning, and scalably deploying our machine learning model. Finally, orchestration and action is handled by serverless function like AWS Lambda. These functions automatically trigger the AI model when new data arrives and execute the predefined actions, such as sending alerts or activating actuators. Next. The strategic advantage of integrating AI is profound. It shifts our entire paradigm from reactivity to proactivity, allowing us to prevent disasters, not just document them. It enables resource optimization, allowing us to focus limited resources like water and personnel where they are needed most. And it provides improved decision support, giving emergency coordinators data-driven visualization and predictions. In conclusion, AI turns our IoT system from a simple data gathering device into a true cognitive partner for building communication resilience. To wrap up our presentation, let's recap the achievements. First, we developed a multi-layered IoT architecture that seamlessly integrated both a smart flood monitoring system and a smart peat forest mitigation system. Second, we selected and justified optimal communication protocols, specifically LoRaWAN and MQTT, for their long-range, low-powered, high reliability characteristics. Third, we've built a secure and fault-tolerant foundation incorporating end-to-end encryption, strong device authentication, and redundant connectivity paths. And finally, we built predictive intelligence with AI and ML, successfully transitioning the system's core capability from reactive monitoring to proactive risk management. This design provides a robust, intelligence, and scalable platform for modern disaster management. And that's all. Thank you.
Thank you.
Thank you. Thank you so much. Well done.